Hello students, welcome to EPG Pathshala. I am Professor Panchapakeshan from the University of Delhi. Today we are going to discuss about the module Quantum Electrodynamics, Particle or Photon Interpretation. This is from the paper Radiation Theory for the Physics course. After studying the module, you should be able to learn to expand the vector potentials in harmonic oscillator plane waves in momentum space and identify the coefficients as creation and destruction operators. You should be able to evaluate the Hamiltonian in terms of creation and destruction operators. You should learn about normal ordering and how normal ordering removes the infinite part of the zero-point energy by its very definition. You should be able to calculate the commutation relation for electric and magnetic fields. You should be able to understand the relation between wave function and the vector potential, learn about Aharonov-Bohm effect and the significance of vector potential in quantum mechanics. You should be able to understand how single-valuedness of the wave function leads to quantization of the flux in a superconducting ring. You should be able to evaluate the interaction Hamiltonian for non-relativistic electron and the electromagnetic field from the Schrödinger equation with the what is called the covariant derivatives. In the last module, we got over the difficulty in quantizing the electromagnetic field by choosing to use the Coulomb or radiation gauge or a transverse gauge for quantizing along with the modification of the Dirac delta function on the right hand side of the commutator to a transverse delta function. In this module, we go ahead and expand the vector potentials and the scalar potential. The scalar potential, of course, here is 0. We expand the vector potentials as plane waves in momentum space and identify the creation and destruction operators. Their commutation relation is similar to the one in the case of the scalar field. We evaluate the Hamiltonian and find it has infinite zero-point energy. We subtract this infinite energy not directly, but by using a normal ordering prescription or what is called a normally ordered Hamiltonian. In the radiation gauge, the four components of the four vectors A mu are reduced to 2. A0 is made to vanish using the gauge freedom, and divergence of A equal to 0 constraints. This constraint reduces the 4 degrees of freedom further to 2. Fermi showed that the longitudinal part of A vector and A0 combine to form the instantaneous Coulomb interaction between the electrons. When non-relativistic electron interacts with the radiation field with 2 degrees of freedom, the two transverse polarizations are the only ones that play a role. The other degrees of freedom are all eliminated and we are left with only 2. We also see the special importance given to the vector potential in quantum theory and discuss the new effect produced. The explanation of this using magnetic field requires a non-local interaction of the magnetic field. So we need the vector potential in quantum mechanics if we want a local theory. This is shown by the Aharonov-Bohm effect. Momentum space expansion of the field as plane waves. We write in the Heisenberg picture, where the operators are time dependent, A vector, which is a function of x vector and time, is equal to integral of d cubed k over 2 pi cubed, square root of that, into square root of 2 omega k, summation over x going to 1 and 2, summation over lambda going to 1 and 2 of epsilon vector k lambda into a k lambda annihilation operator into exponential minus ikx plus a dagger k lambda into exponential plus ikx. K naught, of course, is equal to omega the energy, which is the modulus of the K vector also. K squared, K mu is equal to 0 for the photon. Epsilon vector K1 and epsilon vector K2 are two unit vectors orthogonal to each other, and the propagation vector K and lambda take the values 1 and 2. Epsilon vector K lambda dot K vector is equal to 0, and epsilon 1, epsilon 2 and K vector form a right-handed system as shown on the figure in the right. Epsilon K vector lambda into epsilon K vector lambda prime is equal to delta lambda lambda prime. That is, unless lambda equal to lambda prime, they are orthogonal to each other. And similarly, epsilon K lambda I into epsilon K lambda j summed over all lambdas is equal to delta of ij minus ki of kj. The coefficients ak lambda is identified with destruction or annihilation operator, and a vector, a k vector and lambda or a dagger vector with the creation operator for the quanta of the field. In this case, the quanta of the field are photons. They satisfy the commutation relation, which is the annihilation operator A commuting with creation operator A dagger is equal to delta cubed of k minus k vector times delta of lambda lambda prime vector. And commuter of A with A is 0, commuter of A dagger with A dagger also is 0. The commutation relations follow from those for A mu and its conjugate pi nu. The electric and magnetic fields are related to vector potentials as defined earlier. E vector is minus A vector dot, B vector is equal to divergence cross A vector, as phi, the field scalar potential, is equal to 0 in our gauge. E vector x, the electric field, is minus integral over d cubed k over 2 pi cubed into square root of 2 omega k, summation over lambda equal to 1 to 2, epsilon k lambda upstairs vector into minus I omega k a k exponential minus I k x plus I omega k into a dagger k lambda exponential plus I k x. Hamiltonian and normal ordering. We have seen the Hamiltonian is integral of half E vector squared plus B vector squared d cubed x. This is the total energy of the electromagnetic field. So this can be written as Hamiltonian is equal to half A vector dot whole squared plus curl of A whole squared. Whole thing multiplied by d cubed x and integrated. This is equal to half of A vector dot whole squared plus k vector squared into A vector squared. You can use the vectored identity epsilon ijk into epsilon ilm is equal to delta jikm minus delta jmkl to evaluate curl of A vector whole squared and use divergence of A, that is k dot A is equal to 0 to get the last term above. E vector squared is equal to A dot vector whole squared. This is equal to, there will be a double integral over d cubed k and d cubed prime with the usual denominator, 2 pi cubed into 2 pi cubed for both of them, and 1 divided by square root of 4 omega k prime. Summation over lambda and lambda prime into epsilon k lambda into epsilon k prime lambda prime, and within the bracket we get an I squared omega k omega prime term, a term with minus I squared omega k prime, a term with minus I squared omega k prime, and a term with plus I squared omega k prime. The first term is the product of two annihilation operators, ak and ak prime, and the second one is the product of an annihilation and a creation operator, ak and ak prime dagger. The third term is proportional to ak dagger and ak prime, and the last term is proportional to ak dagger and ak prime dagger. And the coefficients in these cases are, for the multiplication of two annihilation operators, exponential I k plus k prime, and for the creation operators, both of them, it is k plus k prime with coefficient plus I, and for the two cross terms, it will be minus I k minus k prime x and plus I k minus k prime x. On integrating over d cubed x and using the fact that integral over d cubed x 2 pi cubed exponential I k minus k prime x is equal to delta cubed of k minus k prime, we get E vector squared is equal to over d cubed x is equal to d cubed x over 1 over 2 omega k epsilon k lambda into epsilon k lambda prime summation over lambda lambda prime into minus omega k squared into aka minus k term plus omega k squared into aka k dagger term plus omega k squared into ak dagger ak term minus omega k squared into ak dagger term. The second term in the Hamiltonian is, noting that the value of k vector is equal to omega k, as photon mass is 0, the integral over k squared a vector squared d cubed x is given by d cubed x omega k squared by twice omega k summation over lambda and lambda prime delta lambda lambda prime into ak into a minus k exponential minus 2 I omega kt, and two terms with cross terms, and finally the product of two creation operators ak dagger a minus k dagger with exponential 2I omega kt. The Hamiltonian is then given by equation 3.5, that is Hamiltonian is equal to half E vector squared plus k vector squared a squared d cubed x is equal to half summation over lambda, the polarization, integral over d cubed x twice omega k squared omega k ak dagger plus ak dagger ak. So the Hamiltonian H becomes integral over d cubed k summation over lambda ak lambda into ak lambda dagger plus ak lambda dagger into ak lambda, the whole thing multiplied by the energy omega k. This is equation 3.9a, and this gives us the expression half of integral over d cubed k summation over polarization twice ak lambda dagger into ak lambda plus 1, the whole thing multiplied by omega k, or the Hamiltonian H is equal to integral over d cubed k summation over polarization of a dagger k plus half omega k. The half is the crucial extra term that is coming here now. This is related to 0 point energy, and we will relate it to something that we will call normal ordering. We define the zero energy so that the energy in vacuum is 0. For this, we subtract the energy of the vacuum, that is the 0 point energy, from the total energy value. H is equal to H original minus the vacuum expectation value of the Hamiltonian H, which is equal to summation over lambda, the polarization, into omega k, ak dagger ak plus half, minus summation over omega k into half. This is equal to d cubed k into ak dagger ak into omega k. And now we notice the half term, which was the infinite divergent term, has been removed because of the subtraction of the energy of the vacuum. The same thing can be achieved by what is called normal ordering. In normal ordering, the annihilation operators are always moved to the right. The switching is done emitting the 1 by omitting the 1 on the right hand side of the commutation relation. This is a crucial point. We use the commutation relation, but we don't use the term 1 on the right hand side of the commutation relation. This process is called normal ordering. Normal ordering is denoted by colons on both sides, on the left and the right. Thus, colon ak dagger ak plus ak dagger colon complete is equal to ak dagger ak plus ak dagger ak, which is equal to twice ak dagger ak, where we have commuted the second term but have not taken the term 1. Notice we have switched the order in the second term. For a field phi, we separate the positive and negative energy parts and put positive frequency parts on the right. Positive frequency parts are the ones with exponential minus I omega t. Please note, the positive frequency part is exponential minus I omega t. This always goes with A or the annihilation operator. Thus, phi into phi normal ordered is equal to phi minus into phi minus, where phi minus is the negative frequency part and phi plus is the positive frequency part. So it is equal to phi minus into phi minus plus twice phi minus into phi plus phi plus into phi plus, where phi is given by a term which is ak into exponential minus I omega kt, and a term with ak dagger exponential plus I omega kt. So we call these terms as phi with positive frequency. Positive frequency part has minus I omega kt, and phi with minus the negative frequency part, which has got a plus I omega kt. Now the time dependence of the creation and destruction operators are given by exponential minus I omega t and exponential plus I omega t. Normal ordering ensures that the energy of vacuum state is always 0. As destruction operator gives 0 eigenvalue for the vacuum, expectation value of h between the vacuum is equal to 0. EB commutation relation. From the vector potential commutation relations, we can derive the commutation relations for the electric field and the magnetic field. When EIx prime commutes with AJ x vector, this gives us minus I delta transverse of ij x prime vector minus x vector. We use the fact that EI and AJ with I and j being below is equal to I delta ij transverse of x prime vector minus x prime vector, and use only lower indices in the 3 dimensions. Bk is given by epsilon lmk into dl into am. So operate on the left with epsilon ijk di, you get the commutator between ei of xt and exponential ijk dlaj, and this gives us exponential ijk into dl of I operating over the integral d cubed x by 2 pi cubed delta ij minus ki kj divided by k vector squared, the whole thing multiplied by exponential minus I into x minus x prime. The commutator of ei x prime vector t and bk x prime vector t gives us again similarly integral over d cubed k epsilon ljk and 2 terms both with the coefficient plus I kl multiplied by delta ij minus ki kj divided by k vector squared. This comes from the transverse part into exponential minus ik vector into x minus x prime vector. This is equal to minus integral over d cubed k exponential minus ik vector into x minus x prime multiplied by epsilon lik ki minus epsilon ljk into a product of kl, ki and kj divided by k vector squared, and this is equal to 0. Now this is also equal to exponential minus ilk into integral over d cubed k by 2 pi cubed into kl into exponential minus ik vector x minus x prime minus 0. As epsilon ijk kl ki kj is equal to 0, as it is both odd and even in L and J, we get the result that this is equal to 1 over minus I epsilon lik dl delta cube of x minus x prime into minus I epsilon lik dl of delta cube of x minus x prime. So the commutator of Ex x vector t and By x vector t is given by minus I dz of delta cubed of x minus x prime, which is equal to I ddz prime delta cubed x minus x prime, and Ex commuting with Bx is equal to 0. Start. Significance of the vector potential. This is also often called the Aharonov-Bohm effect. In classical electrodynamics, the vector potential has no separate physical significance. It plays its role only through the electric and magnetic fields. However, when we go to quantum mechanics, this is no longer true. The vector potential plays a special role and has its own significance in quantum mechanics. This was shown first by Aharonov and Bohm in 1959 and is called the Aharonov-Bohm effect. Before discussing the details of the effect, we should note that classical electrodynamics is a local theory of electric and magnetic fields. If there are no fields at a point in space, the effect of electromagnetic fields is 0. However, the vector potential can be finite or non-zero at a point where the magnetic field is 0. The effect shows that an electron passing through a point where magnetic field is 0 can still feel an effect if vector potential is not 0 at that point in quantum theory. In terms of magnetic field, it looks like a non-local theory, but in terms of vector potential, it is still a local theory. This should mean that to have a local quantum theory, we must give more importance to vector potential than the magnetic field. Before discussing this effect, we need the expression for wave function in terms of the vector potential. Relation between solutions for zero and finite vector potential. Let us start with the non-relativistic Schrödinger equation, which is p squared by 2m plus v minus e is equal to 0. Using p vector is equal to minus I delta vector, which is equal to minus I di, we have minus I di whole squared by 2m plus v minus e, whole thing operator on psi is equal to 0. This is the Schrödinger equation where we have converted the p part by using I delta. Consider a solution for the wave function psi at a point where the magnetic field is 0. Now, if psi goes to psi with a phase factor exponential minus I lambda x, a local phase change of lambda, which is a function of x vector, the equation 5.1 is invariant if we change to a covariant derivative, as we referred to in the module M2, and make a gauge transformation of field A vector as follows. Minus I di goes to capital Di, which is our notation for the covariant derivative, that is equal to small di, script di, plus I e ai. And ai vector goes to ai plus 1 over e times di lambda. So we have to make two changes. One, the normal derivative goes to the covariant derivative. Other, the vector potential ai goes to a modified vector potential. This is because di, the covariant derivative, which is equal to di plus ie ai plus 1 over e di lambda is equal to operating on psi exponential I lambda x, gives us exponential minus I lambda x in the bracket di psi minus di lambda into psi plus ie into ai psi plus I di lambda into psi, and they all combine to give us exponential minus I lambda as a function of x times di psi. This change, therefore, the covariant derivative remains the same except for the addition of the phase factor that has been done in the psi. This is the reason we call it a covariant derivative, because it is changes exactly like the psi does. Di has the same change as that of the psi. Now if we take di lambda is equal to minus eai, the new ai is equal to 0, and where lambda x is given by minus e, 0 to x vector of vector potential A into ds prime, which is a line integral. For psi at the point 0 is equal to psi nu, which is equal to psi into exponential minus I lambda x, which is equal to psi ie integral over A ds prime, and therefore A nu is equal to 0. Conversely, if psi 0 is the solution for A vector vanishing, that is A vector equal to 0, the solution for finite A is given by psi old form psi 0 into exponential minus IE line integral from 0 to x of A vector dot ds prime vector. So this is the advantage of covariant derivative. And we next go on to discuss what is called the Aharonov-Bohm effect. Consider the double slit geometry with a solenoidal magnetic field for electron interference. A coherent beam, if you look at the figure, a coherent beam from a source on the left of the figure is sent around two sides of a solenoid by a double slit arrangement. The solenoid is in between the two slits. It interferes on the right hand side where the two beams meet. At the point of interference, psi is given by psi 1 plus psi 2, which is psi 0 exponential minus IE, line integral going from 1 to Sx, and the same term with the line integral going from 2 to Sx. By 2 we mean the second path, by 1 we mean the first path. So the line integrals are along the first path and the second path. The phase difference between the two, therefore, can be called delta and is given by E into closed integral of A vector dot ds closed over the path, which is equal to E into B vector into the normal of the vector into ds, which is equal to E into capital phi, where capital phi is the total magnetic flux enclosed by paths A and 2. Here the closed line integral is along path 1 and then along path 2 in the opposite direction. So interference pattern depends on the total flux that is enclosed, even though the electron paths transfers only regions with B vector equal to 0. Classically, the dynamical behavior of electron is given by the Lorentz force, which is 0 when electron path is through points where there is no magnetic field. But in quantum mechanics, there are observable effects due to the magnetic field in regions which are inaccessible to the electron. A is, however, non-zero along the path. So any description in terms of B vector has to be non-local. A local description requires use of A vector and cannot be done adequately with just the B vector. So in quantum mechanics, A vector plays an essential role in this Aharonov-Bohm effect. This was discovered only in 1959 and is a crucial discovery by Aharonov and Bohm. Paths with phase pi, 3 pi give minimum, and paths of maximum of the interference pattern of the wave function is single valued. Quantization of flux. We next consider the magnetic flux enclosed by a superconducting ring, shown in the figure next. At the center, there is a magnetic field due to a solenoid. The solenoid has not been shown in the figure. There is no magnetic field in the ring because this is due to Meissner effect. And if the ring encloses a magnetic flux, then the wave function psi inside the ring is given by psi is equal to psi 0 into exponential minus 2ie line integral 0 to x vector A vector into ds prime. The factor 2 in the exponent now is due to particle in a superconductor not being an electron with charge E, but a Cooper pair with charge 2e. We assume that a Cooper pair behaves like a charged bound particle, even though the pairing is in momentum space. The factor 2 in the exponent is due to the particle of a superconductor not being an electron with charge E, but a Cooper pair with charge 2e. And we assume that a Cooper pair behaves like a particle. Now, if we start from a point in the ring and come back to the same point, the wave function must be single valued, and so same for all the closed paths. This should be so whether or not the closed path includes any flux. This requires the phase change to be multiple of 2 pi. So we require twice E into line integral A vector into ds vector is equal to 2n pi, where n is 0 or plus minus 1 or plus minus 2 or plus minus 3 and so on. So we notice that 2e into the total flux phi is equal to 2n pi or minus n pi divided by E is the value of the flux phi, and so in normal units, if you include the h cross and the c, it is equal to nhc by 2e. The flux trapped in a superconducting ring, therefore, can vary only in steps of h cross c by 2e, whose numerical value is 2.07 into 10 raised to the power minus 7 Gauss into centimeter squared. This quantization of flux has been verified experimentally. Finally, we also show how the interaction of a non-relativistic electron with electromagnetic field can be derived in a simple fashion. The interaction with the electromagnetic field is introduced by changing the normal derivative to the covariant derivative. This is why the covariant derivative is introduced and is extremely useful. All you have to do to bring in the electromagnetic interaction is to use the covariant derivative. And in that case, the covariant derivative of phi, which is d mu plus ie a mu into phi, and a mu is of course phi and minus a vector. Hence, the divergence, the delta of phi is given by delta minus ie a vector of phi, and using minus I delta equal to p or delta vector equal to plus ip or IP into phi is equal to I p vector minus IEA into phi, or p vector going to p vector minus EA vector. So the covariant derivative, what it did, can be also accomplished by changing P0 to P0 minus EA vector and P vector into P vector minus EA vector, or combining them both, P mu into P mu minus EA mu. Thus the Schrödinger equation P vector squared by 2m plus V acting on psi is equal to E psi becomes P vector minus EA vector whole squared divided by 2m plus V acting on psi is E minus A naught into psi. Or we can write it as minus I delta minus EA whole squared by 2m plus V plus EA naught acting on psi is equal to E psi in the form H psi. We write A naught in terms of the electron variables as it is not a dynamic variable. E A naught term is the Coulomb interaction between electrons, which gives H equal to summation over j equal to 1 to n, this is the number of summation over the number of electrons, divided by 1 over 2 mj into pj vector squared minus ea vector whole squared plus summation over I greater than j up to n ei into ej over xi vector minus xj vector plus half integral over e vector transverse squared plus v vector squared plus d cubed x, where E is equal to E transverse is equal to minus A vector dagger. So we can write it as E vector is equal to E transverse vector plus E longitudinal vector with E transverse vector equal to minus A dot vector, and E longitudinal vector is equal to minus delta phi, and divergence of A is equal to 0. A vector is equal to A perpendicular, the A perpendicular the transverse component. A parallel, the longitudinal component, combines with A0 to give the Coulomb interaction between the electrons. So in the Coulomb gauge that we have chosen, we find that the Coulomb interaction separates out and comes separately in the Hamiltonian, whereas the other part, the transverse part, comes in the first term. In this module, we have learned that to expand the vector potentials as harmonic oscillator plane waves in momentum space and identify the coefficients as creation and destruction operators. Evaluate the Hamiltonian in terms of creation and destruction operators. We have learnt about normal ordering and how they remove the infinite part of the 0 point energy by the definition. We calculate the commutation relation for electric and magnetic fields. We understand the relation between wave function and the vector potential. We have learnt about the Aharonov-Bohm effect and the significance of vector potential in quantum mechanics. We understand how single valuedness of wave function leads to quantization of the flux in a superconducting ring. We evaluate the interaction Hamiltonian for non-relativistic electron and the electromagnetic field from the Schrödinger equation with covariant derivatives. Thank you so much.